Assalamualaikum dear students, welcome back to Learn Daily Physics. And today we are starting with third lecture for the magnetic mirror, and this is our final lecture today. So proceeding our lecture, let's talk about what we have done previously. We find out the value for the magnetic moment for the gyration particle, and it was equals to mu is equals to half mv perpendicular square over b. So today we are going to talk we are going to find out that why we've called this magnetic moment. Is this really a magnetic moment? We can prove this value from the definition of a magnetic dipole moment or not, or what's happening around it, and we will find that whether this value is constant or not. Okay, so this is the final lecture of magnetic moment, so let's proceed our lecture. So we have found this value, derived this value previous lecture in part 2 of magnetic mirror. So let's talk about the magnetic dipole moment. The definition of from the definition of the magnetic dipole moment, mu b is equals to a area into the current. Okay, this is the current I, a into current. This is the definition from the definition of a magnetic dipole moment. This is the formula. Okay, so you can find this formula in SSP2 in my course of SSP2. So where we talk about the magnetic properties of matter. So this a is pi r square for a circular loop. How this is equals to pi r square and what is going to happen here, let's talk about let's have a look on a diagram. Okay, I've made this diagram, so let's make it again. So we have a magnetic bottle. Okay, a magnetic bottle like this. Okay, like this. Okay, we have a magnetic bottle like this, and this is along z axis, and b of z is also along the direction of z. So when the particle will enter here, it will start gyration. Okay, it will gyrate like this. Okay, this is the gyration. Okay, now let's say that this is a positive charge and have a charge of positive E. Okay, this charge is positive E and it covers a circle. It completes its one cycle in time period t. This is the time period for one oscillation or for the one circle. Okay, and the area for this loop, for one loop, will be pi r square. Okay, so putting this area is equals to pi r square, this as E, and this equals to T here, because current is equals to charge per unit time. I is equals to Q by T. So rearranging this, we have an equation. This now we have to find out the value of this time period. How we are going to find out the value of this time period? We know that the omega c, the oscillation frequency, is equals to the angular displacement per unit time. Okay, and this theta is equals to 2 pi and 2 pi by t, and from t is equals to 2 pi over omega c. This is a value of t which we are going to put here. Okay, we have put this value here, and we find out this equation, cancelling out pi with pi, and we will have final equation for the mu, this. Okay, then this omega c, we have r square. From this formula, r will be equals to v perpendicular over omega c. V perpendicular, it was r square, so it will be v perpendicular square over omega c square. So omega c will be cancelled out with the 1 omega c in the numerator, and we will have finally our equation v perpendicular over omega c. Putting the value of omega c is equals to qb over m. Putting this value of omega c here, we will have finally our equation which is equals to this equation we have derived there. So it is actually a magnetic moment. Okay, so that's why we can derive this value from the definition of a magnetic dipole moment, and that's why we can say this is a dipole moment. This is a moment, magnetic moment for a gyration particle. So let's next what we are going to do is we are going to find out the value of f of z. Why we are going to find out the value of f of z? Because the main thing what we are going to do is to make a magnetic mirror. I've told you that this particle will go here, okay, and will move backward. It will go this way first, and reaching this wall, let's say there was a coil here and here. Reaching at this coil, it will make a backward direction. It will come here, then it will oscillate like this. Okay, it will gyrate here, here, and then backward. Okay, so this gyration again and again, again and again, again and again is, for that we have to find out this f of z. This f of z will tell us that whether it is going in right direction, how this f of z increases and decreases. To find this f of z, that how it increase and how it decrease, we have to find the value of f of z, what f of z is. So in the previous lecture, in my second lecture, we have find the value of f theta, fr and fz, and this is the value of fz from the previous lecture of mine. And this I wrote this value is equals to m dv by dt. This dv by dt is the parallel acceleration. Okay, so acceleration is equals to dv by dt. So why we are taking the parallel component? The question arises here that why we are taking this parallel component, why we don't written this, why we don't write this v perpendicular or simply v. So the answer for this question is that why we are writing v perpendicular here is that, let's have a look. So again we have a magnetic bottle like this. Oh, not like this. It was like this. Okay, let's say it's like this. So a particle comes and gyrates. Okay, let's say that this is velocity v. Okay, this is its velocity v. This is the velocity component v, and it have some angle here, and this is v perpendicular, and this is v parallel. Okay, and if you don't understand, you have to see the introduction for this. I've shown you in the animation that how gyration occurs, and I've told you what v perpendicular and v parallel is in detail, and in animation you can see how these gyrations are taking place. So this is the value of this v. Let's say this was this v, and it have two components, v perpendicular and v parallel. Now let's say that this is the z direction, and the f of z is the direction is along z axis. So as this f of z is along z axis, so we have to take a velocity which is along the z axis, and which is v perpendicular, because v parallel is along z axis. So for f of z we will take v parallel. So that's why we are taking this v parallel. So now you understand why we put this v parallel here. Okay, the next step what we are going to do is that we are going to write this equation like this. If you take a time derivative of this equation, it will be same equation like this. And here we have a partial z by partial t, partial b of z by partial z mu, like this. This partial z is cancelled out with this partial z here, and the equation, the final equation, we will have this. Okay, this is the final equation. Okay, this is the value of mu. If you put out this value, the equation will be like this. We are not considering that equation, we are considering this as our final equation. So this is our final equation, and we have find out the value of b of z. And if you look closely this equation, the inside of this is half of mv square. What is half mv square? This is the kinetic energy, the parallel component of the kinetic energy. Okay, parallel to what? Parallel to z-axis. This is the time derivative. This factor mu into partial b of z by partial t is equal to the parallel component, the time derivative of the parallel component of kinetic energy. And now let's find out that how this mu is. Now we find out this value. Now we can find that how this mu is constant. Okay, so let's move toward that. So according to the law of conservation of kinetic energy, or simply the law of conservation of energy, E is equals to constant. Kinetic energy is constant. It means that the sum of the kinetic energy is equals to constant. The sum of the kinetic energy parallel plus sum of kinetic energy perpendicular is equals to constant. The parallel factor is this and the perpendicular factor is this. Velocity factor changes, masses are same, mass for the electron is same, and it is equal to the constant. What we are going to do is we are going to take the time derivative on both sides. When we will take the time derivative, our equation will be like this, and when we will take the time derivative of a constant, we know it is equal to 0. The constant of a time derivative is equals to 0. Okay, so the time derivative of a constant is equals to 0. So this term here we have derived is equal to this equation, partial by partial t half mv parallel square. From this equation we have wrote, let's say that this is equation 1, and from equation 1 this value equals to this. Okay, if I've given some equation previously, so change this equation. So from this equation I've told you this value will be equals to minus mu partial b of z by partial t. Okay, now this, how this value is equals to, so this value we know that the value of mu is equals to half mv perpendicular square over b z over b or over b z. So multiplying this b of z here, the mu b of z will be equals to half mv. This value is same as this value, so we can put this value here. Okay, putting this value here, mu of b instead of this value, we will have this. So now applying the product rule, this mu partial b of z will be equals to b of z partial mu by partial t. This is the product rule we have applied here. This all of value will be cancelled out with this one, and the remaining value will be b of z partial mu by partial t. This b of z will go this way and it will be equals to 0. B of z will be 0. So we will have partial mu by partial t equal to 0. We know that this factor, when this factor is equals to 0, then this value will, when we will take integral, or we also know that this factor means that it is a constant. Mu is a constant term because its time derivative equals to 0. So it is a constant, mu is a constant term. Now we find out this mu is a constant term. The next thing what we are going to do is that we are going to find out how a charged particle confines inside a magnetic bottle. Okay, how inside it confines. So how a magnetic mirror confines a charged particle. So you understand how this is constant. This term is used in the next to say that the charged particle is confined. So we know that V parallel is along V of Z. Let's make another diagram. Let's try to make it like this. You can see. Okay. Let's make it here on the board. It will be more prominent to you. So we have a bottle like this. Okay, let's make a bigger one. Like this. Okay, it's a candy. So a charged particle here enters and have two components. V, this is V perpendicular and V parallel. V perpendicular and V parallel. This is Z axis. Okay, and the direction, we know that the gradient is along, this is B of Z is applied toward this, and our gradient is also parallel to this B of Z. Okay, I'm not making all of the gyration. Let's not talk about that. So V perpendicular is perpendicular to B of Z from this equation, and V parallel is parallel to B of Z. That's why we are calling it parallel and perpendicular, because they are parallel and perpendicular to B of Z. Now what we have seen that mu is constant, our magnetic moment is constant. When the magnetic moment is constant, what this equation means? Okay, this equation means that putting this value of mu equals to constant, we will be multiplied here with the constant, and when we will remove this constant, so equality will change into the proportionality, and this proportionality means that the B magnetic field applied B of Z, or B magnetic field, is directly proportional to this factor. Okay, and what this factor is, this factor is the kinetic energy of the perpendicular component. Okay, this is the same kinetic energy of the perpendicular component, and this factor, you can say, is as the kinetic energy is constant. We have seen that law of conservation is applicable, and this kinetic energy is constant. It means that by increasing this factor will decrease. Okay, because kinetic energy is equals to constant, this factor will increase and this factor should decrease. Okay, by increasing this one should decrease. Now what happens? We have a direct relation of magnetic field B with this kinetic component. Okay, let's have a look at what I'm trying to say. I'm trying to say is B is directly proportional to the kinetic energy perpendicular. Okay, and let's see that in the magnetic mirror or in the magnetic bottle, what is the variation in B. Okay, so here the B was strong. In my first lecture I've told you that B is strong because the field lines are closer here. B is strong, and B is weak here because the field lines are more farther in this region. Okay, so strong, weak, and then strong. It means that as B is strong here, which means the kinetic energy, the perpendicular factor of kinetic energy is strong, or is the value of the kinetic energy is high here. And as this value increase from this formula, the total kinetic energy is conserved. It means that if the kinetic energy of the perpendicular component increases, then the kinetic energy of the parallel factor will decrease. Here it is strong, the perpendicular factor is strong, which means the parallel factor is weak, and the parallel factor is responsible for the direction, for the movement of the particle along Z axis. because V parallel is responsible for the particle to move in Z axis. As this kinetic energy is minimum, this will be maximum, this kinetic energy will be minimum. It means that this approaches to infinity, this approaches to zero, which means that the particle cannot move further in Z direction. Okay, it cannot move any further in Z direction, so it will move backward again. And then what happen, then V parallel will, here V parallel will be at the maximum value, and V perpendicular will be minimum. What I'm trying to say is, in Urdu or in Hindi, I'm trying to let's elaborate you in that, कि जब आपके पास काइनेटिक एनर्जी का परपेंडिकुलर कंपोनेंट यहाँ और यहाँ बढ़ जाएगा तो पैरेलल कंपोनेंट कम हो जाएगा. क्यों कम हो जाएगा? कि आपके पास ये जो फैक्टर है काइनेटिक एनर्जी, क्योंकि कांस्टेंट है, कांस्टेंट का मतलब ये है कि एक चीज़ बढ़ेगी तो दूसरी कम होगी, नेट जो आपके पास रिजल्ट आएगा वो कांस्टेंट होगा. ठीक है, कि 10 रुपये हैं आपके पास, ठीक है, तो उन 10 रुपये का क्या है कि टोटल ओवरऑल 10 रुपये हैं दो भाइयों के पास. अगर एक के पास 8 हैं तो दूसरे के पास 2 होंगे, एक के पास 2 हैं तो दूसरे के पास, एक के पास 9 है तो दूसरे के पास 1 होंगे. ओवरऑल क्या होगा? एक के पास 10 हैं तो दूसरे के पास क्या होगा? कुछ भी नहीं होगा. तो ये 10 क्या है? V परपेंडिकुलर यहाँ पे 10 है, V परपेंडिकुलर यहाँ पे मैक्सिमम है, तो जो V पैरेलल होगा वो यहाँ पे क्या आ जाएगा? 0 हो जाएगा. यहाँ पे वो रुक जाएगा, यहाँ पे वो ट्रैप हो गया, इससे आगे वो नहीं जा सकेगा. वो क्या करेगा? यहाँ पे V पैरेलल 0. एंड देन व्हाट हैपन्स, this kinetic energy is dominant here over this one, and it will move backward, and same reason will occur again and again, and it will make a charged particle to confine inside a bottle. Okay, so this is how we confine a charged particle inside a bottle. This is a perfect machine. We can say that this is a machine, but it can't completely confine a particle, because the parallel component won't get 0. Some of the particle escapes from here, and we will talk about later that how to overcome that. But our magnetic mirror is now complete. Now we have our magnetic mirror topic is complete. I hope you understand what I was trying to say, and you understand everything very clearly. And thank you very much for your time, and assalamu alaikum.